The National Electrical Code, specifically Section 230.40 Exception 3, addresses the conditions under which service conductors can be installed underground without overcurrent protection. This exception is narrowly defined and hinges on the concept of same premises. To understand this, it's crucial to dissect the key terms and requirements within the relevant NEC articles. Firstly, the term service conductors refers to the conductors extending from the service point to the service disconnecting means. The service point is the point of connection between the facilities of the serving utility and the premises wiring. The service disconnecting means is the device or devices used to disconnect all conductors in a building or other structure from the service entrance conductors. Secondly, overcurrent protection generally involves the use of devices such as circuit breakers or fuses to protect conductors and equipment from excessive current that could cause overheating or damage. Overcurrent protection is a fundamental safety requirement in electrical installations. Thirdly, the phrase same premises is pivotal. The NEC doesn't explicitly define same premises universally, leading to interpretations based on the specific context and the authority having jurisdiction or AHA. Generally, it implies that the buildings or structures being supplied are closely associated and under the same ownership or management. The distance between the structures is a significant factor. If buildings are separated by a considerable distance, they are less likely to be considered on the same premises. Now, let's consider NEC 230.3, which states that one building shall not be supplied through another. This rule prevents creating a daisy chain of power distribution, which can introduce safety hazards and complexities in overcurrent protection and coordination. The main concern here is the potential for overloading the conductors feeding the first building, especially if the second building has a substantial electrical load. Now let's consider the scenario where service conductors run from a meter underground to another building 100 feet away without overcurrent protection. According to the NEC, specifically considering the information provided and the interpretation of same premises, this setup is generally not acceptable without overcurrent protection at the source. The 100-foot separation between the buildings typically places them outside the scope of being considered on the same premises. Therefore, the service conductors feeding the second building must have overcurrent protection. The overcurrent protection device, such as a circuit breaker or fuse disconnect, should be located at the point where the conductors receive their supply. This ensures that the conductors are protected against overloads and short circuits. Consider this example: a house and a detached garage are 100 feet apart. The service conductors run from the meter in the house to the garage without any overcurrent protection at the house. Because of the 100-foot separation, the garage is not considered to be on the same premises as the house. Therefore, the service conductors to the garage must be protected by an overcurrent device located at the house. There are several factors to consider when determining whether buildings are on the same premises. Firstly, ownership. Are the buildings under the same ownership or management? Secondly, function. Are the buildings functionally related? Thirdly, separation. What is the physical distance between the buildings? Fourthly, access. Is there unrestricted access between the buildings? Fifthly, local codes and interpretations. Local electrical codes and interpretations by the AHA can influence the determination. Now let's consider a 200 amp service. According to NEC Table 310.16, the minimum size copper conductor for a 200 amp service is 3/0 American wire gauge or AWG, assuming a 75°C termination temperature rating. If aluminum conductors are used, the minimum size is 4/0 AWG. The overcurrent protection device should be rated at 200 amps or less. If the load calculation for the second building is significantly less than 200 amps, the overcurrent protection device can be sized accordingly, but it should not exceed the ampacity of the conductors. Now let's look at NEC 240.4, which covers protection of conductors. This section specifies that conductors must be protected against overcurrent in accordance with their ampacities. The ampacity of a conductor is the maximum current, in amperes, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Now let's look at the installation requirements for underground service conductors. These conductors must be installed in accordance with NEC 230.30, which covers underground service conductors. This section specifies the minimum burial depths for underground service conductors, which vary depending on the voltage and the type of raceway or cable used. For example, direct buried conductors operating at 600 volts or less must be buried at a minimum depth of 24 inches. If the conductors are encased in concrete, the minimum burial depth can be reduced to 18 inches. Now let's talk about voltage drop. When running conductors over a long distance, voltage drop can become a concern. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to increase the size of the conductors. Now, let's consider a situation where there are multiple buildings on a single property. The NEC allows for multiple buildings to be supplied from a single service, but there are specific requirements that must be met. Each building must have a disconnecting means located at or near the point where the service conductors enter the building. The disconnecting means must be readily accessible and capable of being locked in the open position. The service conductors to each building must be protected by an overcurrent device. The size of the service conductors must be based on the total load of all the buildings being supplied. Now let's explore some common mistakes to avoid when installing service conductors. Firstly, undersized conductors. Using conductors that are too small for the load can cause overheating and potentially lead to a fire. Always perform a load calculation to determine the appropriate conductor size. Secondly, improper overcurrent protection. Using an overcurrent device that is too large for the conductors can allow excessive current to flow, damaging the conductors and creating a safety hazard. Always select the correct size overcurrent device based on the conductor ampacity. Thirdly, inadequate grounding. Proper grounding is essential for electrical safety. Ensure that the grounding system is installed correctly and that all equipment is properly grounded. Fourthly, failure to comply with local codes. Local electrical codes may have additional requirements that must be met. Always check with the local authority having jurisdiction before starting any electrical work. Fifthly, neglecting voltage drop. Long conductor runs can result in excessive voltage drop, which can cause equipment to malfunction. Calculate the voltage drop and increase the conductor size if necessary. Now let's consider the importance of coordination between the overcurrent devices. Coordination ensures that the overcurrent device closest to the fault will trip first, minimizing the extent of the outage. If the overcurrent devices are not properly coordinated, a fault in one building could cause the entire service to trip, affecting all the buildings connected to it. Coordination studies are often performed for large or complex electrical systems to ensure proper protection and selective coordination. Now let's talk about surge protection. Surge protection devices or SPD protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD should be installed at the service entrance and at any sensitive electronic equipment. The NEC requires surge protection for certain types of installations, such as dwelling units. Now let's look at arc fault circuit interrupters or SIs. SIs are circuit breakers that are designed to protect against arc faults, which are a common cause of electrical fires. SIs detect arc faults by monitoring the current waveform and tripping the circuit breaker when an arc fault is detected. The NEC requires SIs in many areas of dwelling units, such as bedrooms and living rooms. Now let's consider ground fault circuit interrupters or GFCIs. GFCIs are devices that protect against ground faults, which occur when current flows through an unintended path to ground. GFCIs detect ground faults by monitoring the current balance between the hot and neutral conductors. If there is an imbalance, the GFCI trips the circuit, interrupting the flow of current. The NEC requires GFCIs in many areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Now let's consider the importance of proper labeling. All electrical panels and equipment should be clearly labeled to identify the circuits and equipment they serve. This helps to prevent confusion and makes it easier to troubleshoot problems. The NEC requires specific labeling requirements for electrical panels and equipment. Now, let's talk about the importance of regular maintenance. Electrical systems should be inspected and maintained regularly to ensure that they are operating safely and efficiently. Regular maintenance can help to identify potential problems before they become serious. The NEC recommends regular inspections of electrical systems. Now let's discuss the role of a qualified electrician. Electrical work should always be performed by a qualified electrician who is licensed and insured. A qualified electrician has the knowledge and experience to perform electrical work safely and in compliance with the NEC and local codes. Hiring a qualified electrician can help to ensure the safety and reliability of your electrical system. Now let's delve into the specifics of applying NEC 230.40 Exception 3 in various scenarios. Firstly, consider a multi-tenant commercial building. If the service conductors are run underground to each tenant space, are they considered to be on the same premises? Generally, yes, because the entire building is under single management and the tenants are all part of the same commercial operation. However, each tenant space must have its own disconnecting means and overcurrent protection. Secondly, consider a campus environment with multiple buildings. In a college or corporate campus, the buildings are typically considered to be on the same premises because they are part of a unified institution and under common management. Underground service conductors can be run between buildings without overcurrent protection at each building, provided that the overall service has adequate overcurrent protection. Thirdly, consider a residential subdivision with shared amenities. If homes in a subdivision share a common area with a community center, pool, or other amenities, are these considered to be on the same premises? Typically, no. Each residence is considered a separate premises, and any service conductors running to the shared amenities must have overcurrent protection. Fourthly, consider agricultural settings with outbuildings. Farms often have multiple outbuildings such as barns, sheds, and workshops. If these buildings are all part of the same agricultural operation and under the same ownership, they might be considered to be on the same premises, depending on the AHJ interpretation. However, it is still best practice to provide overcurrent protection at each building. Now let's explore the potential hazards of running service conductors without overcurrent protection. Firstly, overload. Without overcurrent protection, the conductors can be subjected to sustained overloads, causing them to overheat and potentially melt the insulation. This can lead to short circuits and fires. Secondly, short circuit. A short circuit can cause a sudden and massive flow of current, which can quickly damage conductors and equipment. Without overcurrent protection, the fault current can continue to flow until the conductors burn open, creating a significant fire hazard. Thirdly, ground fault. A ground fault occurs when current flows through an unintended path to ground. Without overcurrent protection, the ground fault can cause electric shock hazards and equipment damage. Fourthly, voltage surge. Voltage surges caused by lightning strikes or other events can damage conductors and equipment. Without surge protection, the surge can propagate through the entire electrical system, causing widespread damage. Now let's discuss the different types of overcurrent protection devices. Firstly, circuit breakers. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent is detected. They can be reset after tripping, making them a convenient and reliable form of overcurrent protection. Secondly, fuses. Fuses are single-use devices that interrupt the flow of current by melting a fusible link when an overcurrent is detected. Fuses are simple, inexpensive, and provide reliable overcurrent protection. However, they must be replaced after they blow. Thirdly, molded case circuit breakers or MCCBs. MCCBs are heavy-duty circuit breakers that are used in high-current applications. They are designed to withstand high fault currents and provide reliable overcurrent protection. Fourthly, insulated case circuit breakers or ICBs. ICBs are high-performance circuit breakers that are used in critical applications where reliability is paramount. They offer advanced features such as adjustable trip settings and communication capabilities. Now let's consider the factors that influenced the selection of overcurrent protection devices. Firstly, ampacity. The overcurrent protection device must be rated to handle the ampacity of the conductors it is protecting. Secondly, interrupting rating. The overcurrent protection device must have an interrupting rating sufficient to interrupt the maximum available fault current at the point of installation. Thirdly, voltage rating. The overcurrent protection device must be rated for the voltage of the electrical system. Fourthly, time current characteristics. The time current characteristics of the overcurrent protection device must be coordinated with the other overcurrent devices in the system to ensure selective coordination. Fifthly, environmental conditions. The overcurrent protection device must be suitable for the environmental conditions in which it will be installed, such as temperature, humidity, and corrosive atmospheres. Now let's discuss the importance of proper installation techniques for service conductors. Firstly, proper trenching. Underground service conductors must be installed in trenches that are deep enough to meet the minimum burial depth requirements of the NEC. The trench must be free of rocks, debris, and other sharp objects that could damage the conductors. Secondly, proper backfilling. The trench must be backfilled with suitable material that will not damage the conductors. The backfill should be compacted to prevent settling and protect the conductors from physical damage. Thirdly, proper support. Service conductors must be properly supported to prevent strain on the connections and terminals. Support should be spaced according to the manufacturer's instructions and the requirements of the NEC. Fourthly, proper termination. Service conductors must be properly terminated at the service disconnecting means and other equipment. The terminations must be clean, tight, and corrosion-free. Fifthly, proper identification. Service conductors must be properly identified to indicate their purpose and voltage. Identification can be achieved using color coding, labeling, or other approved methods. Now let's consider the implications of using different types of conductors for service entrances. Firstly, copper conductors. Copper conductors have a high conductivity and are resistant to corrosion. They are a popular choice for service entrances, but they are more expensive than aluminum conductors. Secondly, aluminum conductors. Aluminum conductors are less expensive than copper conductors, but they have a lower conductivity and are more susceptible to corrosion. When using aluminum conductors, it is important to use connectors and terminations that are specifically designed for aluminum. Thirdly, copper-clad aluminum conductors. Copper-clad aluminum conductors consist of an aluminum core with a copper cladding. They offer a compromise between the cost of aluminum and the conductivity of copper. Now let's discuss the requirements for service entrance cable or SEC. SEC is a type of cable that is specifically designed for use as service entrance conductors. SEC is typically available with either copper or aluminum conductors. The NEC specifies the requirements for the construction, installation, and use of SEC. Now let's consider the use of ground rods and grounding electrodes. Ground rods are used to provide a low impedance path to ground for electrical systems. The NEC specifies the requirements for the installation of ground rods and other grounding electrodes. Ground rods must be driven into the ground to a minimum depth of 8 feet and must be spaced at least 6 feet apart. Now let's discuss the importance of bonding. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current. Bonding helps to reduce the risk of electric shock and equipment damage. The NEC specifies the requirements for bonding electrical systems. Now let's consider the use of surge arresters. Surge arresters are devices that protect electrical equipment from voltage surges caused by lightning strikes or other transient events. Surge arresters are typically installed at the service entrance to protect the entire electrical system. The NEC recommends the use of surge arresters in areas where lightning strikes are common. Now let's discuss the requirements for working space around electrical equipment. The NEC specifies the minimum working space that must be provided around electrical equipment to allow for safe operation and maintenance. The working space must be clear of obstructions and must have adequate lighting. Now let's consider the importance of personal protective equipment or PPE. Electrical workers should always wear appropriate PPE when working on energized electrical equipment. PPE includes items such as rubber gloves, safety glasses, and insulated tools. The use of PPE could help to protect electrical workers from electric shock, burns, and other injuries. Now let's discuss the importance of lockout/tagout procedures. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the power source, locking the disconnecting means in the open position, and tagging the disconnecting means to warn others not to energize the equipment. Now let's consider the implications of using renewable energy sources such as solar panels or wind turbines. When using renewable energy sources, it is important to ensure that the electrical system is properly designed and installed to safely integrate the renewable energy source. The NEC contains specific requirements for the installation of renewable energy systems. Now let's discuss the importance of energy efficiency. Energy-efficient electrical systems can help to reduce energy consumption and save money. Energy-efficient equipment such as LED lighting and high-efficiency motors can significantly reduce energy costs. The NEC contains requirements for energy-efficient electrical systems. In conclusion, adhering to the NEC and best practices for service conductors and overcurrent protection is crucial for electrical safety and reliability. Always consult with a qualified electrician and the local authority having jurisdiction to ensure compliance with all applicable codes and regulations.